There's a rule in astronomy that nobody talks about, but everyone knows. When something moves away from the sun, it fades. It's not a theory. It's not a guess. It's physics. Simple, predictable, undeniable physics. The farther an object travels from the sun's heat, the colder it gets. The less light it reflects. The dimmer it becomes in our telescopes. Comets do this. Asteroids do this. Every piece of rock and ice that's ever crossed our solar system has followed this rule without exception. Until now. It's mid-October 2025. 6 weeks have passed since 3I Atlas made its closest approach to the sun. Perihelion, they call it. The turning point, the moment when an interstellar visitor swings past our star and begins its long journey back into the void. By now, 3I Atlas should be fading, growing dimmer with every passing day, slipping quietly into the darkness between worlds. But it's not. Instead, something impossible is happening. It's getting brighter. The first person to notice was Dr. Elena Vasquez, an astronomer working the graveyard shift at the Cerro Tololo Inter-American Observatory in Chile. She wasn't supposed to be looking at 3I Atlas that night. Her team had moved on to other targets. The interstellar visitor had already passed perihelion weeks ago, and the data from that event was still being processed. But Elena had a habit of checking old targets, just to see. Just to make sure. She pulled up the brightness measurements from the past week and compared them to the predictions. Then she stopped. She zoomed in on the graph, checked the timestamps, ran the calibration again. The numbers didn't make sense. According to the data, 3I Atlas had brightened by nearly 15% over the past 10 days. That shouldn't be possible. Elena leaned back in her chair, staring at the screen. She felt the kind of confusion that comes right before understanding, the moment when your brain knows something is wrong but hasn't figured out what yet. She ran the analysis again. Same result. She checked the telescope's calibration logs. No errors. She pulled up archived images from 2 weeks ago and compared them to tonight's observation. The difference was unmistakable. 3I Atlas was brighter. At first, she didn't tell anyone. Not because she wanted to keep it secret, but because she didn't trust it yet. In astronomy, anomalies are usually mistakes. A bad pixel, a miscalibration, a cosmic ray that hit the detector at just the wrong moment and made something look brighter than it really was. You don't announce a discovery until you've ruled out every possible error. So Elena spent the next 3 hours checking everything. She examined the raw data frame by frame. She compared her results to other telescopes that had observed the same region of sky. She even called a colleague in Hawaii to see if their instruments had picked up anything unusual. They had. The Mauna Kea Observatory had recorded the same brightness increase. So had the European Southern Observatories. Very large telescope in Chile. So had a dozen smaller observatories scattered across the southern hemisphere. Every telescope that looked at 3I Atlas saw the same thing. It was getting brighter, and that meant it wasn't a mistake. By October 5th, the news had spread through the astronomy community like a slow-burning fire. Not in headlines, not in press releases, but in emails, in Slack messages, in late-night phone calls between scientists who had known each other for decades and who spoke in the kind of shorthand that only comes from years of shared work. Have you seen the 3I data? Yeah. What do you think? I don't know. I've never seen anything like it. The conversations were cautious. Nobody wanted to overreact. Nobody wanted to be the one who jumped to conclusions and ended up looking foolish. But beneath the caution, there was something else. Unease. Because the brightness increase wasn't just unexpected, it was wrong. It violated the basic physics of how comets behave. When a comet approaches the sun, it heats up. Ice turns to gas. The gas escapes in jets, forming a glowing cloud around the nucleus called a coma, and sometimes a tail that streams behind it. That's what makes comets bright. But when a comet moves away from the sun, the process reverses. The heating stops. The outgassing slows. The coma fades. The brightness drops. That's the rule. 3I Atlas was breaking it. Dr. Yuki Tanaka, an orbital dynamicist at the Japan Aerospace Exploration Agency, was one of the first to model what the brightness curve should have looked like. He plugged in the object's mass, its distance from the sun, its estimated composition. He accounted for outgassing, dust ejection, and solar radiation pressure. He ran the simulation 3 times to make sure the math was right. The results were clear. 3I Atlas should have been fading at a rate of about 2% per week. Instead, it was brightening at nearly the same rate. Yuki stared at the graph on his screen. The predicted curve was a smooth downward slope, exactly what you'd expect from a comet moving away from the sun. The observed data was the opposite, an upward slope, steady, consistent, undeniable. He sent the results to his colleagues with a single sentence in the subject line. We need to talk about this. By October 8th, the global astronomy community was paying attention. Observatories that had moved on to other projects began redirecting their instruments back toward 3I Atlas. Radio telescopes started listening for emissions. Infrared satellites scanned for thermal signatures. Everyone wanted to know the same thing. What was making it brighter? The obvious answer, the one that everyone tried first, was outgassing. Maybe 3I Atlas was still releasing gas and dust, even 6 weeks after perihelion. Maybe it had pockets of volatile ices buried beneath its surface that were only now being exposed. Maybe it was rotating in a way that brought fresh material into sunlight, but the numbers didn't support that. For outgassing to explain the brightness increase, 3I Atlas would need to be releasing enormous amounts of material, tons of it, every day. And if that were happening, telescopes would see a coma, a cloud of gas and dust surrounding the object. They didn't. Images from the Hubble Space Telescope showed 3I Atlas as a sharp, bright point of light. No coma, no tail, no diffuse halo of gas. Just the object itself, glowing steadily in the dark. Dr. Marcus Webb, a spectroscopist at the Harvard-Smithsonian Center for Astrophysics, ran a detailed analysis of the light coming from 3I Atlas. He was looking for absorption lines, the fingerprints of specific molecules like water, carbon monoxide, or methane. If the object was outgassing, those molecules would show up in the spectrum. They didn't. The spectrum was almost featureless, clean, reflective. It looked less like a comet and more like polished metal. Marcus sat in his office, staring at the data, trying to make sense of it. He'd spent 20 years studying comets. He'd seen hundreds of spectra. He knew what they were supposed to look like. This wasn't it. He picked up his phone and called a colleague. "I think we have a problem," he said. By mid-October, the whispers had turned into conversations, and the conversations had turned into something else. Concern, not panic, not yet, but a quiet, growing realization that something fundamental was happening, something that didn't fit into any existing model. Astronomers began sharing their data openly, bypassing the usual process of peer review and publication. This was too important to wait, too strange to keep quiet. A pattern emerged. Every telescope that observed 3I Atlas confirmed the same thing. The object was still brightening, not rapidly, not exponentially, but steadily, predictably, as if following some internal clock that had nothing to do with the sun's heat. The rate of brightening was roughly 1.5% per week. That might not sound like much, but in astronomy, where objects millions of kilometers away are supposed to follow predictable rules, a 1.5% weekly increase is enormous. It meant something was actively adding energy to the system. Something was pushing light toward us. On October 14th, NASA issued a brief statement. It was careful, measured, the kind of language that governments and space agencies use when they want to acknowledge something without alarming anyone. Astronomers continue to monitor interstellar object 3I Atlas as it moves outbound from the inner solar system. Recent observations have detected an unexpected increase in brightness. Teams are working to determine the cause. There is no threat to Earth. The statement was technically accurate, but it left out the most important part. Nobody knew what was causing the brightness increase. Every natural explanation had been tested and found insufficient. Outgassing couldn't explain it. Dust ejection couldn't explain it. Reflected sunlight couldn't explain it. And that left only one possibility. Something unnatural. Dr. Avi Loeb, the Harvard astrophysicist known for his controversial theories about interstellar objects, was one of the first to say it out loud. "We need to consider the possibility," he said in an interview, "that 3I Atlas is not a natural object." The comment sparked debate. Some scientists agreed. Others pushed back, arguing that jumping to exotic explanations before exhausting natural ones was premature. But beneath the debate, a deeper question was forming. If 3I Atlas wasn't outgassing and it wasn't reflecting more sunlight, then where was the brightness coming from? Was it changing shape? Unfurling some kind of reflective surface? Was it emitting its own light, powered by something internal? Or was it doing something we didn't have the vocabulary to describe yet? The data kept coming in. Every night, telescopes across the globe turned toward 3I Atlas and recorded its light. Every morning, astronomers woke up to new measurements, new graphs, new confirmation that the anomaly was real. And every day the object got a little brighter. By the third week of October, the brightness had increased by nearly 25% since perihelion. That was impossible. And yet there it was, in the data, undeniable. Elena Vasquez, the astronomer who had first noticed the anomaly, sat alone in her office one night, staring at the light curve on her screen. She'd spent weeks checking and rechecking the data, weeks ruling out errors, weeks hoping for a natural explanation that made sense. But the more she looked, the more certain she became. Something was happening out there, something we'd never seen before. She thought about the object itself, a visitor from another star system, a traveler that had crossed the void for thousands, maybe millions of years, carrying with it the chemistry and history of a place we would never see. And now, 6 weeks after passing the sun, it was glowing brighter, as if waking up, as if responding to something, as if it knew we were watching. The question hung in the air, unspoken but impossible to ignore. If outgassing stops when a comet moves away from the sun's heat, then what is still pushing light toward us from the cold and the dark? And the only answer anyone could give was the one nobody wanted to say. We don't know. Act 2. Patterns in the void. The human brain is wired to see patterns. It's how we survived, how we learned which plants were safe to eat, how we knew when storms were coming, how we tracked seasons and predicted harvests. We look at clouds and see faces. We look at stars and draw constellations. We find meaning in randomness because that's what keeps us alive. But sometimes the pattern isn't in our heads. Sometimes it's real. And when astronomers started looking closer at 3i Atlas over the past few days, they found something that made every natural instinct scream that this wasn't random at all. The brightness wasn't just increasing, it was pulsing. Dr. Sarah Chen was the first to notice it. She's a postdoctoral researcher at MIT, analyzing light curve data that's been coming in since the brightness anomaly was confirmed earlier this week. Her job is simple: measure how bright 3i Atlas appears over time and plot the results. She expected to see a steady upward trend, the kind of smooth curve you get when something is gradually getting brighter for reasons nobody understands yet. That's not what she found. Instead, the brightness oscillated. It rose and fell in waves. Small variations, barely noticeable at first, but consistent. Regular. On October 6th, Sarah zoomed in on the data, focusing on a 5-day window going back to when the object passed perihelion. The pattern was unmistakable. 3i Atlas brightened over a period of roughly 47 hours, reaching a peak, then dimmed slightly before brightening again. The cycle repeated, over and over, like clockwork. She checked the timestamps, ran the analysis 3 different ways, used 2 separate datasets from different telescopes. Same result. 47 hours, plus or minus 20 minutes. Sarah sat back in her chair, staring at the graph. Her heart was beating faster than it should have been, because she knew what this meant. Objects in space tumble, they rotate. And when they rotate, their brightness changes depending on which side is facing you. That's normal, that's expected. But natural tumbling isn't this precise. Asteroids wobble, comets spin unevenly because their surfaces are irregular, their masses distributed asymmetrically. Their rotation periods drift over time due to outgassing, tidal forces, and the chaos of their own motion. This wasn't that. This was... She didn't want to use the word. Not yet. But the data didn't care what she wanted. The pulse was regular, mathematical, precise. October 7th, Sarah's discovery was confirmed by teams in Europe, Japan, and Australia. Everyone saw the same 47-hour cycle. At observatories around the world, astronomers began coordinating their observations, timing their telescope pointings to catch 3i Atlas at different phases of its brightness cycle. The European Southern Observatory's Very Large Telescope in Chile, the Subaru Telescope in Hawaii, the Hubble Space Telescope in orbit above Earth. All of them turned toward 3i Atlas. All of them recorded the pulse. Dr. James Okoye, an astrophysicist at the University of Cambridge, is part of the coordination effort. He spent years studying variable stars, objects whose brightness changes due to internal processes like pulsation or eclipses. He knows what regular variability looks like, and this is too regular. Natural rotation periods drift, he said during a video conference with his colleagues yesterday afternoon, even by tiny amounts, but this, it's holding steady. 47 hours, 12 minutes, give or take a few minutes for measurement error. Someone on the call asked the question everyone was thinking. Could it be artificial? James hesitated. I don't know, he said. But if it's natural, it's following physics we've never seen before. The next breakthrough came from thermal imaging. NASA's Stratospheric Observatory for Infrared Astronomy, a modified Boeing 747 that flies at 45,000 feet to observe the universe in wavelengths that don't penetrate Earth's atmosphere, was redirected to study 3i Atlas earlier this week. The goal was simple: measure the object's temperature. If it's outgassing, if jets of gas are escaping from its surface, those jets should show up as hotspots in infrared light. The night before last, the aircraft made its first pass. Dr. Amelia Torres sat in the cramped instrument bay, monitoring the data as it streamed in. Outside, the sky was black and endless. Inside, screens glowed with false color images of the infrared sky. 3i Atlas appeared as a small, bright dot, and around it something impossible. Hotspots, not just one, not random, but multiple points of heat arranged in what looked almost like a grid. Amelia leaned closer to the screen, adjusting the contrast. The hotspots weren't constant. They appeared, glowed brightly for a few hours, then faded. New ones emerged in different locations, but not randomly. They cycled. As 3i Atlas moved through its 47-hour brightness period, different sections of its surface heated up and cooled down in sequence. It was like watching a pattern of lights turning on and off. Amelia recorded everything. When the flight landed early yesterday morning, she sent the data to her colleagues with a single sentence. "This isn't outgassing. I don't know what this is." The thermal data changed everything. Outgassing would produce random hotspots wherever jets of gas broke through the surface. You'd see asymmetric heating, chaotic variations, the kind of messy thermal signature you get when ice turns to vapor and escapes in unpredictable bursts. This was the opposite. The hotspots appeared in coordinated sequences, almost like a pattern, almost like something activating and deactivating in a controlled way. Dr. Yuki Tanaka, who had modeled the brightness predictions last week, spent yesterday running simulations to see if any natural process could explain it. He tried everything: rotating surface features, subsurface ice pockets that heated and vented in cycles, reflective patches that caught sunlight at different angles. None of it worked. The thermal pattern was too organized, too precise. He sent his results to the team yesterday afternoon with a note. "We need to consider non-thermal explanations," which was a polite way of saying this might not be natural at all. Yesterday, October 25th, the global astronomy community was in full coordination mode. Radio telescopes are listening, spectroscopes are dissecting the light. Infrared observatories are tracking the thermal pulses. Hubble is capturing high-resolution images during different phases of the brightness cycle. Everyone is searching for the same thing: an explanation. Anything that makes sense. What they're finding instead is more mystery. Spectroscopic analysis, the method of splitting light into its component wavelengths to identify what an object is made of, is revealing something strange. Dr. Marcus Webb at Harvard, the same spectroscopist who had noticed the featureless spectrum last week, ran a detailed comparison of 3I Atlas's light signature during different phases of its pulse cycle. The results came in yesterday morning, and they're unsettling. At the peak of brightness, the spectrum shows strong reflectivity in wavelengths consistent with metal or crystalline structures, the kind of signature you'd expect from polished aluminum or silicon. But during the dimmer phase, the reflectivity shifts. Different wavelengths dominate. Different materials seem to be facing Earth. It's as if the object's surface is changing, or as if different parts of it are rotating into view, each made of something different. Marcus has studied hundreds of asteroids and comets. He's seen iron meteorites, carbonaceous chondrites, icy bodies rich in organics. He's never seen anything that changes its spectroscopic signature this dramatically over a 47-hour cycle. He wrote up his findings and sent them to the international team a few hours ago. His conclusion is cautious but clear. The surface composition of 3I Atlas is inconsistent with any known natural body. Right now, this morning, the scientific community is facing a reality they haven't prepared for. Every natural explanation is failing. It's not tumbling randomly. The pulse is too regular. It's not outgassing. There's no coma, no tail, no spectroscopic evidence of volatiles. It's not reflecting sunlight in predictable ways. The thermal hotspots don't match solar heating patterns. It's not a simple rotating rock. The spectroscopy shows surface changes that don't fit any known mineral composition. So what is it? The question hangs over every conference call, every data review session, every conversation between scientists who are starting to feel like they've stepped into something they weren't trained for. Dr. Avi Loeb, never one to shy away from controversial ideas, said it plainly in an interview yesterday with Science magazine. When you've ruled out everything natural, you have to consider the unnatural. This object is behaving like a machine. The comet is already sparking backlash. Other scientists are calling it premature, reckless, sensational. But privately, in emails and group chats happening right now, more and more astronomers are starting to wonder the same thing. The coordination effort is intensifying by the hour. Observatories are operating in shifts, ensuring 24-hour coverage. As 3I Atlas sets below the horizon for telescopes in Chile, it rises for observers in Australia. When Australia loses sight of it, Hawaii takes over. The goal is to capture every second of the pulse cycle, every thermal shift, every spectroscopic change. Because if this is a machine, if this is something artificial, then understanding its rhythm is the first step to understanding its purpose. Dr. Sarah Chen, who discovered the pulse just a few days ago, finds herself at the center of a global collaboration. She's coordinating data from a dozen observatories, compiling light curves, tracking the thermal patterns. She's barely slept in 48 hours. Every time she closes her eyes, she sees the graph. The regular repeating pulse. 47 hours. Over and over, like a heartbeat. The night before last, exhausted and running on coffee, she said something to a colleague that she immediately regretted. "What if it's not reflecting light?" she asked. "What if it's generating it?" Her colleague looked at her. "You mean like internal power?" Sarah nodded slowly. "I mean, what if the brightness cycle isn't about what's facing the sun? What if it's about something inside the object turning on and off?" The room went quiet. Because if that's true, if 3I Atlas has an internal energy source, then it's not a comet at all. It's something else entirely. Yesterday morning, the James Webb Space Telescope completed a detailed scan of 3I Atlas. The data is still being processed, but preliminary results are already circulating among the team, and they're stunning. The thermal map shows the object in unprecedented detail, and the hotspots are undeniable. They're not random, they're not chaotic, they form patterns, geometric patterns, lines of heat that appear and disappear in sequence, almost like circuits activating. Dr. Amelia Torres, who captured the first thermal images the day before yesterday, is staring at her screen right now in silence. She spent her entire career studying comets. She's seen hundreds of them. She knows what they're supposed to look like. This isn't a comet. She doesn't know what it is, but it's not natural. It's Friday afternoon now, October 26th, 2025. Less than a week has passed since the brightness anomaly was first discovered, and in these few days, everything has changed. The scientific consensus is fracturing in real time. Some researchers are clinging to the hope that a natural explanation exists, that they just haven't found it yet. Others are beginning to accept the possibility that 3I Atlas is something humanity has never encountered before. An object that crossed the void between stars. An object that pulses with mathematical precision. An object whose surface shows coordinated thermal activity and spectroscopic signatures inconsistent with any known material. An object that might not be a rock at all. The data is clear. The patterns are real. And the question that nobody wants to ask out loud is becoming impossible to ignore. Are we watching a natural object behaving in ways we don't understand? Or are we watching something that was built? Dr. James Okoye sits alone in his office right now, looking at the pulse data from the past week. 47 hours, regular, consistent, unwavering. He thinks about natural cycles, the rotation of planets, the orbits of moons, the pulsation of stars. All of them drift. All of them vary, even slightly, because the universe is messy and chaotic, and nothing stays perfectly regular forever. Except this. He pulls up the data and measures the pulse period with the highest precision his instruments allow. 47 hours, 12 minutes, 34 seconds. Every single cycle over the past week. No drift, no variation. James feels something he hasn't felt in years of studying the cosmos. Fear. Not the fear of danger, but the fear of not understanding. The fear that comes when you realize the universe has rules you've never seen before, or when you realize you're looking at something that follows rules of its own. It's October 26, 2025. 6 days since the anomaly was discovered, and right now today, astronomers around the world are facing a truth they never expected. The patterns are too precise to be random. The thermal sequences are too coordinated to be chaos. The pulse is too regular to be natural. When something repeats with precision across millions of kilometers of void, you're either seeing the heartbeat of a machine, or the universe teaching us physics we were never meant to learn. And right now, in these quiet observatories scattered across the globe, scientists are starting to believe it might be the first. The question is no longer whether 3I Atlas is unusual. The question is whether it's alive. Act 3. The geometry of doubt. There's a difference between motion and intention. A rock thrown into space will follow a path determined by gravity. It obeys Newton's laws. It doesn't think. It doesn't choose. It simply goes where the mathematics say it must go. But when something changes its path, when something adjusts its velocity, even slightly in ways that gravity alone can't explain, then you're no longer looking at a rock. You're looking at something that moves with purpose. And over the past 24 hours, astronomers have discovered something that's making them question everything they thought they knew about 3I Atlas. The object isn't just pulsing, it's steering. Dr. David Kim is an orbital dynamicist at NASA's Jet Propulsion Laboratory in Pasadena, California. His job is to track objects in space and predict where they'll go. Asteroids, comets, spacecraft, anything that moves through the solar system. He's good at it. He's been doing it for 15 years. A few days ago, on October 23rd, when the brightness anomaly was first confirmed, David started running updated trajectory models for 3I Atlas. The math should have been straightforward. The object passed perihelion on October 30th. This date is now a little messy as we shifted everything back, but we'll leave it as a fixed point in the past narrative for now. Its velocity, direction, and orbital elements were well established from weeks of observations before perihelion. All David had to do was plug in those numbers and calculate where the object would be in the coming days and weeks. The model should have matched reality. It didn't. By October 25th, after getting new positional data from multiple observatories, David noticed something wrong. 3I Atlas wasn't where it was supposed to be, not by much. Just a tiny offset. A few thousand kilometers. In the vastness of space, that's almost nothing. A rounding error. The kind of discrepancy you get from measurement uncertainty or slight variations in solar radiation pressure. But David checked the measurements. They were solid. He ran the trajectory model again, this time accounting for every known force: solar gravity, planetary perturbations, radiation pressure, even the tiny push from outgassing, though there was no evidence of it. Still, the model didn't match. 3I Atlas was deviating from its predicted path, and it was doing it in a very specific way. David brought the data to his supervisor yesterday morning, October 25th. "Something's pushing it," he said, pointing at the trajectory plot on his screen. His supervisor, Dr. Rachel Soto, leaned in to look. "How much?" she asked. "Small, very small, maybe 0.02 millimeters per second squared, but consistent." Rachel frowned. 0.02 millimeters per second squared is tiny. It's about 100,000th of Earth's gravity. Barely a whisper of force, but in space, tiny forces add up. Over days and weeks, a gentle push can shift an object's path by millions of kilometers. "Could it be outgassing?" Rachel asked. David shook his head. "That's what I thought at first. But look at the direction." He pulled up a 3D visualization of 3I Atlas's trajectory through the solar system. The predicted path was a smooth hyperbolic curve, sweeping past the sun and heading back out into interstellar space. The actual path showed small deviations, but those deviations weren't random. They were all in the same general direction. Prograde. Forward along the velocity vector. "It's accelerating," David said quietly. "Not much, but it's speeding up." Rachel stared at the screen. "Send this to the trajectory team," she said. "I want confirmation from independent analysis." By yesterday evening, October 25th, 3 separate teams had confirmed David's findings: JPL in California, the European Space Agency's Operations Center in Germany, and the International Astronomical Union's Minor Planet Center in Massachusetts. All of them saw the same thing. 3I Atlas was experiencing non-gravitational acceleration. Small, consistent, directional. The object was pushing itself forward, adding velocity in a way that couldn't be explained by gravity alone. Dr. Yuki Tanaka in Japan, who had been tracking this object since the brightness anomaly was discovered, ran his own analysis overnight. He didn't just look at where 3I Atlas was now. He projected where it would be if the acceleration continued. What he found made him sit up straight in his chair at 3 a.m. If the acceleration persisted for just a few more days, the object's trajectory would shift enough to bring it closer to Earth's orbital plane. Not dramatically closer, not dangerously closer, but closer. And the geometry was troubling. This morning, October 26th, NASA convened an emergency meeting. Not public, not announced. Just a quiet video conference with mission planners, trajectory specialists, and planetary defense coordinators. David Kim presented his findings. "The acceleration is real," he said. "We've confirmed it across multiple observation sets. The magnitude is approximately 0.02 millimeters per second squared, sustained over at least the past 72 hours. Someone asked the obvious question. Could it be outgassing? David pulled up the spectroscopic data that had come in from Harvard yesterday. No evidence of volatiles, no coma, no dust, and the direction is wrong. Outgassing jets push randomly depending on where the gas vents. It's almost perfectly prograde. Meaning? Meaning it's pushing in the exact direction that would increase the object's velocity along its orbital path. That's not how natural outgassing works. The room went quiet. Dr. Rachel Soto spoke up. We need to model intercept scenarios. Worst-case assumptions. If the acceleration continues, what does the trajectory look like in 2 weeks? In a month? David nodded. Already working on it. Preliminary results suggest that if current trends hold, the object's closest approach to Earth on December 6th could shift from 270 million kilometers to something closer. How much closer? Still calculating, but we're talking tens of millions of kilometers. Not a collision risk, but closer than we predicted. Another voice on the call. And if the acceleration increases? David hesitated. Then all bets are off. At the same time, across the Atlantic, the European Space Agency was running their own analysis. Dr. Sophia Lindström, a trajectory specialist at ESA's Operations Center in Darmstadt, Germany, was looking at the same data, but she was asking a different question. Not just how much is it accelerating, but why this direction? She pulled up a simulation of the solar system, a 3D model showing the positions of planets, the Sun, and 3I Atlas's trajectory. Then she added something else, Earth's future position, where Earth would be in 1 week, 2 weeks, 3 weeks. And what she saw made her breath catch. The tiny velocity changes. 3I Atlas was experiencing. They were aligning its path with Earth's orbit. Not perfectly, not precisely, but the geometry was undeniable. Every small push was bringing the object's trajectory closer to intersecting the plane where Earth travels around the sun. Sophia ran the numbers 3 times. Same result. She saved the file and immediately sent it to her supervisor with a subject line that said simply, "We need to talk." By this afternoon, October 26th, internal memos were circulating at NASA and ESA. Not public statements, not press releases. Just quiet documents marked internal use only and preliminary analysis. But someone leaked them. A low-resolution scan of a PDF appeared on a private forum used by amateur astronomers and space enthusiasts. Then it spread. Reddit, Twitter, specialized space blogs. The document was a trajectory analysis from JPL, dated October 26, 2025. It showed 3i Atlas's predicted path under 3 scenarios. No further acceleration. Object continues on current trajectory. Closest approach to Earth, 270 million kilometers on December 6th. Current acceleration continues at 0.02 mm s2. Closest approach, potentially reduced to 180-200 million kilometers. Acceleration increases. Closest approach, unknown. Further modeling required. At the bottom of the document in small text was a note. Mission planning team to model intercept windows and potential response scenarios. Classification, preliminary assessment only, not for public distribution. The internet exploded. Dr. Avi Loeb was interviewed by CNN at 4 p.m. today. "The trajectory shifts are real," he said. "Multiple agencies have confirmed them. The question is what's causing them." The interviewer asked, "Could it be natural?" Avi paused. "Natural outgassing would produce random directional changes. What we're seeing is directional bias. The object is accelerating in a specific direction that happens to bring it closer to Earth's orbital plane. That's unusual." "Are you saying it's steering toward us?" "I'm saying the geometry is consistent with course correction. Whether that's intentional or some natural process we don't understand yet, I can't say. But the data are clear. Something is changing this object's velocity, and the changes are not random." Right now, this evening, astronomers around the world are grappling with 2 possibilities. Either 3i Atlas is experiencing some natural phenomenon that produces directional, sustained acceleration, without outgassing, without visible thrust, and without any mechanism we've ever observed before. Or it's doing something deliberate. Dr. Sarah Chen, who discovered the 47-hour pulse, is on a conference call right now with the International Observation Team. "We need to track this hour by hour," she says. "If the acceleration is linked to the pulse cycle, if it's happening at specific phases, that tells us something." Someone else asks, "What if it's not constant? What if it's adjusting?" The call goes silent. Because if 3i Atlas is adjusting its thrust, if it's making micro-corrections based on some internal calculation, then they're not watching a rock anymore. They're watching something that navigates. Dr. David Kim is still at his desk at JPL. It's evening now in California. He should have gone home hours ago. But he can't stop looking at the trajectory data. He's added Earth's position to his visualization. Not just where Earth is now, but where it will be over the next several weeks. And he's overlaid 3i Atlas's path. The 2 curves are getting closer. Not intersecting, not yet. Maybe not ever, but closer. And every time he updates the model with new positional data, the gap shrinks a little more. David thinks about what it would take to steer an object across interstellar space. First, you'd need to know where you're going. That means sensors, instruments, the ability to measure your position and velocity relative to your destination. Second, you'd need propulsion, something to change your course. Something subtle enough that it doesn't produce visible exhaust or heat, but powerful enough to matter over millions of kilometers. Third, you'd need time, patience, the ability to make tiny corrections over weeks and months, trusting that the math will bring you where you need to be. And fourth, you'd need a reason. David stares at the screen. 3i Atlas is 1.8 astronomical units from Earth right now, about 270 million kilometers. In November, that distance will shrink, unless the acceleration stops. Unless whatever is pushing it decides to stop. Late tonight, ESA issued a statement. Brief, measured, carefully worded. Recent orbital analysis of interstellar object 3i Atlas has detected small non-gravitational accelerations consistent with natural solar radiation effects. Trajectory predictions remain well within safe parameters. There is no threat to Earth. Observations continue. NASA released a similar statement an hour later, but astronomers who read them noticed what they didn't say. They didn't explain the directional bias. They didn't mention the geometry. They didn't address why the acceleration is perfectly aligned with the object's velocity vector, the one direction that would most efficiently change its trajectory. It's late now. October 26, 2025. The observatories are still watching. The telescopes are still tracking. and the data is still coming in. Every 6 hours, new positional measurements. Every update, a new trajectory calculation. And every calculation shows the same thing. 3i Atlas is accelerating, slowly, gently, precisely, in the exact direction needed to bring its path closer to Earth's orbit. The mathematics are undeniable. Something is changing this object's velocity by fractions of a meter per second, and every change brings its future path closer to intersecting our orbit, as if the void itself is learning where we'll be. Dr. Sophia Lindstrom sits alone in her office in Germany, looking at the trajectory plot. She's tried every natural explanation she can think of: solar wind pressure, magnetic interactions, thermal recoil from uneven heating. None of them fit. The acceleration is too consistent, too directional, too purposeful. She opens a new file and types a single sentence. If 3i Atlas is correcting course, then who or what is steering it, and why does its geometry keep pointing toward us? She saves the file. She doesn't send it to anyone. Not yet. Because once you ask that question out loud, you can't take it back. And right now, on October 26, 2025, that question is the only one that matters. Ace-Tiefra. Signal and silence. There's a frequency that astronomers call the universal channel. 1.420 gigahertz. It's not arbitrary. It's not chosen by humans. It's physics. That's the frequency at which neutral hydrogen atoms emit radio waves naturally. Hydrogen, the most abundant element in the universe. The building block of stars. The signature of cosmic chemistry. Every civilization that builds radio telescopes discovers this frequency. Every species that learns to listen to the cosmos hears hydrogen singing at 1.420 gigahertz. It's called the water hole, a quiet band in the radio spectrum where natural noise is minimal and signals can travel cleanly across the void. If you wanted to send a message that any technological civilization would recognize, if you wanted to say we are here in a language that transcends biology and culture, you would broadcast at 1.420 gigahertz. And yesterday afternoon, something did. Dr. Michael Torres has been working at the Very Large Array in New Mexico for 12 years. The VLA is a collection of 27 radio dishes spread across the high desert plains, each one 25 meters wide, arranged in a Y-shaped configuration that stretches for miles. Together they act as a single massive telescope, listening to the radio whispers of the universe. Most days the work is routine, monitoring pulsars, mapping distant galaxies, cataloging radio sources. Yesterday is not most days. At 3:47 p.m. Mountain Time, October 26, 2025, one of the monitoring systems flagged an anomaly. Michael was in the control room, reviewing data from an observation of a quasar, when the alert appeared on his screen. Unscheduled detection. Strong signal. Direction: ecliptic coordinates consistent with 3i Atlas. Frequency: 1.420 GHz. Michael stared at the screen. His first thought was interference. Someone's radio transmitter, a satellite passing overhead. Ground-based noise leaking into the system. He checked the interference filters, all active, all functioning normally. He checked the satellite tracking database. No satellites in the beam at that time. He pulled up the raw data stream. The signal was real, and it was coming from the direction of 3i Atlas. Michael's hands moved quickly across the keyboard, pulling up analysis tools, starting recording protocols, flagging the data for immediate review. The signal wasn't constant. It pulsed, modulated, rose and fell in intensity. It lasted 11 minutes. Then it stopped. Just stopped. As if someone had flipped a switch. Michael sat in his chair, heart pounding, staring at the spectrogram on his screen. He'd been doing this for 12 years. He'd seen thousands of signals. Natural radio emissions from stars, planets, gas clouds, artificial signals from human satellites and ground stations. He knew the difference between noise and structure. He knew this had structure. He picked up the phone and called his supervisor. "We need to talk," he said. "Right now." Within an hour, the data had been sent to 3 other radio observatories. Parkes Observatory in Mbemikwarp, Australia, Jodrell Bank in England, the Green Bank Telescope in West Virginia. All of them reviewed the signal independently. All of them reached the same conclusion. The signal was real, it was structured, and it came from the direction of 3i Atlas. Dr. Jill Tarter, a veteran of SETI research and one of the world's leading experts on technosignature detection, was brought into the analysis at 5:30 p.m. She reviewed the data in silence, her expression unreadable. After 20 minutes, she looked up. "This isn't natural," she said quietly. Someone asked, "Are you sure?" Jill pulled up the frequency analysis. Natural radio emissions have broad spectra. Noise spreads across many frequencies. This is narrowband, focused, and look at the modulation pattern. She zoomed in on a section of the signal. The intensity varied in regular peaks and valleys. Not random, not chaotic, mathematical. "This is information," Jill said. I don't know what it's saying, but it's structured, deliberate. The room went quiet, because everyone in that room knew what that meant. By 6 o'clock p.m., news of the detection had spread through the global SETI network. Not publicly, not yet, but through secure channels connecting research institutions that had spent decades listening for exactly this kind of signal. The Breakthrough Listen Project at Berkeley, the SETI Institute in California, the Arecibo Legacy Group that had continued monitoring after the telescope's collapse. Every organization that had ever searched for extraterrestrial intelligence was now looking at the same data, and they were all asking the same questions. Is it real? Is it artificial? Is it from 3i Atlas? Dr. Sofia Martinez at the SETI Institute ran a detailed analysis of the signal structure. She looked for patterns, repetitions, mathematical sequences. What she found was subtle but unmistakable. The signal contained repeating elements, short bursts separated by precise intervals. The intervals followed a pattern: 2, 3, 5, 7, 11 seconds. Prime numbers. Sophia felt her breath catch. Prime numbers aren't random. They're mathematical constructs, and using them as a pattern in a signal is a classic SETI concept. A way to demonstrate intelligence, to show that the signal is artificial, not natural. She immediately sent her findings to the analysis team. Subject line: the signal is intentional. By 7 p.m., the decision was made. If this was a signal, if something out there was broadcasting, then humanity should respond. The question was how. The VLA could broadcast as well as receive. It could send radio waves in any direction, at any frequency. But what do you say to something 270 million kilometers away that just spoke to you in prime numbers? Dr. Michael Torres and his team quickly designed a response signal. Simple, clear, unmistakable. A transmission at 1.420 GHz, the same frequency the signal came in on. The content, a sequence of prime numbers followed by a mathematical pattern representing the IWI structure of a hydrogen atom, followed by Earth's location relative to the sun. Basic, universal. The kind of thing any civilization with radio astronomy would understand. At 7:23 p.m. Mountain Time, the VLA transmitted. The signal was broadcast toward the coordinates where 3i Atlas currently sits, 1.8 astronomical units from Earth. At the speed of light, the transmission would take about 15 minutes to reach the object, if there was a receiver, if something was listening, if it wanted to respond. Everyone in the control room watched the clock. 7:30 p.m., 7:40 p.m., 7:50 p.m. The minimum time for a round-trip communication, signal there, signal back, would be about 30 minutes. They waited. 8 p.m., 8:15 p.m., 8:30 p.m. Nothing. Just the normal background hiss of the radio cosmos, pulsars ticking, distant galaxies murmuring, but no response, no acknowledgement, no reply. By 9 p.m., observatories around the world had also tried. Greenbank broadcast at 8:05 p.m. Eastern Time. Parkes broadcast at 11 a.m. Australian Eastern Time, which was evening in the U.S. Jodrell Bank broadcast at 1:30 a.m. Greenwich Mean Time. Everyone sent variations of the same message: mathematical patterns, prime numbers, hydrogen signatures, universal greetings in the language of physics. All of them waited for a response. None came. The silence was deafening. Dr. Jill Tarter sat in her office tonight, looking at the signal data on her screen. She'd spent 40 years searching for signals like this. Decades of listening to the cosmos, hoping to hear something that wasn't noise, wasn't natural, wasn't us. And now she had it. A signal. Structured, mathematical. Coming from an interstellar object that was already showing impossible behavior. But the object wasn't responding to their transmissions. It had spoken once at 3:47 p.m., and then gone silent. Jill thought about what that meant. There are two kinds of signals in the universe: beacons, which broadcast continuously, announcing presence, inviting contact, and probes, which listen, measure, observe, but don't engage. This felt like the second. The signal wasn't a greeting. It wasn't an invitation to dialogue. It was a measurement, a ping, like sonar, like radar. Send a signal. Wait for the echo. Learn about your environment. And then, go silent, because you've learned what you needed to know. Dr. Sofia Martinez reached the same conclusion independently. She was looking at the timing of the signal. 11 minutes, that wasn't random. 11 minutes is enough time to sweep a wide area, to sample the radio environment around Earth, to detect our transmissions, our satellites, our radio leakage, to measure us. And the frequency choice, 1.420 GHz, wasn't about communication. It was about being heard. Broadcasting at the hydrogen line guaranteed that any civilization with radio astronomy would notice, would pay attention, would know the signal was artificial. It was a test, and we responded. Which means whatever sent that signal now knows. Something it didn't know before. It knows we're here. It knows we're listening. It knows we're capable of responding. Sophia wrote up her analysis and sent it to the SETI network at 9:45 p.m. tonight. Her conclusion: we are not being contacted, we are being studied. By 10 p.m., NASA held an emergency virtual briefing. Participants included trajectory specialists, radio astronomers, SETI researchers, and planetary defense coordinators. The question on everyone's mind: what do we do now? One scientist suggested continuing to broadcast. Keep trying to establish communication. Another argued against it. If it's not responding, we're just revealing more about ourselves, our capabilities, our technology, our intentions. A third voice: maybe that's the point. Maybe it already got what it needed. Dr. Rachel Soto from JPL spoke up. Let's look at what we know. The object shows coordinated thermal patterns, regular brightness pulses, trajectory adjustments, and now a radio signal that carried mathematical structure but stopped after 11 minutes. All of this suggests, she paused, intentionality, purpose, and the purpose seems to be observation, not interaction. Someone asked, so what does it want? Rachel's answer was simple and chilling. Information. It's collecting data. About us. About Earth. About whether we're here and whether we're paying attention. And now it knows, someone said quietly. It's late now, October 26th, 2025, almost midnight. The observatories are still listening. The radio dishes are still pointed at 3i Atlas. But there's been no second signal, no response to the broadcasts. Just silence. Dr. Michael Torres is still in the VLA control room, staring at his monitors, waiting for something that might not come. He thinks about the signal. 11 minutes of structured radio emission at the most recognizable frequency in the universe. A signal that announced itself clearly. A signal that stopped. A signal that didn't want a conversation. And he realizes something that makes his skin cold. A signal that speaks without wanting an answer is not a greeting. It's reconnaissance, a measurement taken from the dark. And whatever sent it already knows we heard. Across the world tonight, astronomers are coming to the same realization. 3i Atlas isn't trying to talk to us. It's studying us. It sent a signal to see if we'd notice, to see if we'd respond, to measure our capabilities. And we did exactly what it expected. We noticed. We analyzed. We responded. We showed it everything it needed to see. Now it knows. It knows we have radio astronomy. It knows we understand the hydrogen line. It knows we can detect and interpret structured signals. It knows we're here, and it's still silent. Dr. Jill Tarter sits alone in her office, looking out at the night sky. Somewhere out there, 270 million kilometers away, an object is moving through the solar system, pulsing, accelerating, observing, and now silent. She thinks about all the years spent listening for signals, all the hopes that first contact would be a conversation, a dialogue, a meeting of minds across the cosmic void. But this isn't that. This is one way. We're not being invited to communicate. We're being cataloged. And the most unsettling part? Whatever is out there already has all the information it needs. The signal proved it. It knows we heard. It knows we responded. It knows we're watching it, and it's choosing not to respond. Because it doesn't need to. It already knows everything it came to learn. Tonight, October 26, 2025, humanity learned something new about the universe. We are not alone, but we are also not equals. Somewhere in the dark, something is watching, measuring, learning. And when it got what it needed, it simply stopped talking. A signal that speaks without wanting an answer is not a greeting, it's reconnaissance. A measurement taken from the dark, and whatever sent it already knows we heard. The question now isn't whether we're being observed. The question is, what happens next? ACT, the human response. There's a moment in every discovery when it stops being science and becomes something else. When it stops being data on a screen and becomes a truth that changes everything. When it stops being a question and becomes an answer we weren't ready to hear. Tonight, October 26, 2025, humanity crossed that threshold. For hours, the radio signal from 3i Atlas was contained. Known only to astronomers, to SETI researchers, to the quiet rooms where telescopes hum and data streams across monitors. But containment doesn't last. Not in the age of the internet, not when the truth is this big. By 10:30 p.m., the first leak appeared. A tweet from someone who claimed to work at the VLA. No name. Anonymous account created an hour earlier. We detected a signal from 3i Atlas, 1.420 GHz, 11 minutes, mathematical structure. This is real. Within minutes, it had been retweeted 1,000 times, 10,000, 100,000, and humanity woke up to a truth it had been denying for a week. We are not alone. The news spread like fire across dry grass. Reddit threads exploded, Twitter erupted, Facebook groups formed in minutes, thousands of people joining, sharing, speculating. Major news networks scrambled to verify the story. CNN called the VLA, no comment. BBC contacted NASA. We're reviewing data and will issue a statement shortly. Al Jazeera reached out to ESA. Observations are ongoing, no threat to Earth. But the non-answers were answers enough. By 11 p.m. Eastern Time, CNN broke the story with a chyron that would define the night. Breaking, radio signal detected from interstellar object 3I Atlas. The anchor's voice was steady, professional, but you could hear the tremor underneath. We're receiving reports that radio telescopes in New Mexico and possibly other locations have detected what appears to be a structured radio signal coming from the interstellar visitor known as 3I Atlas. We're working to confirm details, but multiple sources are telling us this signal showed mathematical patterns consistent with artificial origin. The world stopped. Dr. Elena Vasquez, the astronomer in Chile who first detected the brightness anomaly 6 days ago, was at home when her phone started ringing. News outlets, colleagues, friends, family, everyone asking the same questions. Is it real? Is it aliens? What does it mean? Elena sat on her couch, phone buzzing nonstop, and felt the weight of what was happening. A week ago, she'd noticed an anomaly, a data point that didn't fit, a brightness increase that shouldn't exist. Now the whole world was watching. She turned on the TV. Every channel was covering it. Split screen showing telescopes, graphics of 3I Atlas's trajectory, talking heads debating what this meant for humanity. On CNN, a panel of scientists was trying to explain the signal. The frequency, 1.420 gigahertz, is significant, one of them said. It's the hydrogen line, a natural frequency that any civilization with radio astronomy would recognize. Using this frequency suggests intentionality. But why isn't it responding to our transmissions? The anchor asked. The scientist hesitated. We don't know. It's possible the signal wasn't meant for us, or it was a probe, a measurement, and once it got the data it needed, it stopped. A measurement of what? Of us, of whether we're here, of our capabilities. The anchor's expression changed. You could see the realization settling in. So we're being studied? It's one interpretation, yes? On social media, the reaction split into camps almost immediately. Some people were celebrating. We're not alone. This is the greatest discovery in human history. First contact. Others were terrified. What do they want? Are we in danger? This is how every sci-fi horror movie starts. And some were skeptical. It's probably just a natural phenomenon. The government is hiding something. This is a distraction. But underneath all the noise, there was something else. A shared feeling. A collective moment of recognition. Everything had changed. The universe wasn't empty. And something out there knew we existed. At 11:45 p.m., the White House press secretary issued a brief statement. The president has been briefed on the radio detection from interstellar object 3I Atlas. U.S. government agencies, including NASA and the Department of Defense, are coordinating with international partners to analyze the data. There is no indication of any threat to national security or public safety. We will provide updates as more information becomes available. The statement was calm, measured, designed to prevent panic. But the fact that the Department of Defense was mentioned sent a clear message. This wasn't just science anymore. This was a security matter. Within the Pentagon, a different conversation was happening. The National Space Defense Center in Colorado Springs had been monitoring 3I Atlas since the trajectory. Adjustments were detected yesterday. Now, with the radio signal confirmed, the object had moved from scientific curiosity to potential unknown asset. Military analysts were running scenarios. What if the object is a probe? What if it's gathering intelligence? What if it decides to change course? There were no protocols for this, no playbook, no historical precedent. How do you respond to something from another star system that's observing you? The answer for now was carefully. At the European Space Agency's Operations Center in Germany, Dr. Sophia Lindstrom was in a meeting that had been going for 3 hours. ESA's crisis management team, representatives from member states, trajectory specialists, communication experts, everyone trying to figure out what comes next. We need a unified response, someone said. If we're going to communicate with this object, it should be a coordinated effort, not individual nations acting independently. But it's not responding, another voice pointed out. We've broadcast multiple times, nothing. Maybe we're not saying the right thing. Or maybe it doesn't want to talk. Sophia spoke up. She'd been quiet most of the meeting, listening, processing. What if this isn't about communication, she said. What if the signal was never meant to start a conversation? The room turned to her. Think about it, she continued. It broadcasts for 11 minutes. Mathematical structure, prime numbers, then stops, doesn't respond to our replies. That's not how you start a dialogue. Then what is it? It's a test, or a scan. It sent a signal to see what would happen, to see if anyone would notice, to measure the response, and now it has that data. Someone asked, so what do we do? Sophia looked around the room. We accept that we might not be in control of the situation. We're not the ones asking questions. We're the ones being studied. The silence that followed was heavy. In Tokyo, Dr. Yuki Tanaka was giving an interview to NHK, Japan's national broadcaster. The interviewer asked, Dr. Tanaka, you've been tracking this object since the beginning. What should people know? Yuki chose his words carefully. 3i Atlas is displaying behavior we've never seen in any natural object. The brightness pulses, the trajectory adjustments, and now a radio signal. Each piece of evidence on its own might have a natural explanation, but together, they suggest something coordinated, something intentional. Are you saying it's artificial? I'm saying we should consider all possibilities, and one possibility is that this object is not a random piece of debris from another star system. It might be something designed, something sent. Sent by whom? Yuki paused. That's the question, isn't it? And right now we don't have an answer. By midnight, the United Nations Secretary General issued a statement. The detection of a potential signal from interstellar object 3i Atlas represents a moment of profound significance for all, humanity. The United Nations calls for international cooperation, transparency, and calm as we work to understand this phenomenon. This is not a matter for any single nation. It concerns all of us collectively as a species. It was diplomatic, idealistic, the kind of statement the UN was built to make. But in living rooms and bars and streets around the world, people weren't thinking about international cooperation. They were thinking about what it meant. Some gathered in groups, talking late into the night. In New York, people stood in Times Square, looking up at the sky. In London, crowds gathered near the Royal Observatory. In Mumbai, families watched the news together, processing what this meant for their understanding of existence. Others were alone, staring at screens, reading everything they could find, trying to make sense of the impossible. And everyone, everywhere, was asking the same questions. What is it? What does it want? What happens next? Dr. Avi Loeb appeared on multiple news networks tonight, one interview after another. On Fox News. We should take this seriously. The evidence is compelling. This object is not behaving like a comet or an asteroid. On MSNBC. The radio signal is significant. It suggests the object has active systems, sensors, possibly communication technology. On BBC World, we need to prepare for the possibility that we're not alone in the universe, and more importantly, that we're visible. Some scientists criticized him for being too definitive, for jumping to conclusions, but Avi didn't care. Someone has to say it, he told a colleague between interviews. Someone has to acknowledge what the data are showing. We can't pretend this is normal. In the SETI Institute's offices in California, Dr. Jill Tarter was fielding calls from journalists, researchers, and government officials. Everyone wanted to know, is this first contact? Her answer was consistent. First contact implies mutual recognition, a conversation. What we have is a signal that was sent, but not continued. It's more like first detection. We've detected something artificial, but we haven't made contact. What's the difference? Contact requires two parties engaging. This is one-sided. We're aware of them. They're aware of us. But there's no dialogue. Is that concerning? Jill paused. It's significant. If they're observing without engaging, it suggests a purpose we don't understand yet. At 12:30 a.m., a group of philosophers and ethicists at Oxford University released an open letter. It was titled, Humanity's Response to Observed Intelligence. The letter argued that if 3i Atlas was indeed artificial, humanity needed to consider not just scientific questions, but ethical ones. What are our obligations to unknown intelligence? How should we respond to observation without consent? What does it mean for human autonomy if we're being studied? And most importantly, what kind of species do we want to be when we know someone is watching? The letter went viral because it asked the questions that people were feeling but couldn't articulate. We'd spent centuries wondering if we were alone. Now we knew we weren't. But instead of joy, instead of relief, many people felt something else. Vulnerability. The feeling of being seen by something we couldn't see back. By 1 a.m. on the East Coast, exhaustion was setting in. But most people couldn't sleep. How do you sleep when the universe just changed? Dr. Sarah Chen, who discovered the brightness pulses, sat in her apartment in Cambridge scrolling through social media. She saw the speculation, the fear, the excitement, the denial, and she thought about the data, the 47-hour pulse, the thermal patterns, the trajectory adjustments, the radio signal. Each piece fit together like a puzzle revealing a picture she never wanted to see. This wasn't random. This was designed, and whatever designed it was out there right now, 270 million kilometers away, continuing its journey through our solar system, still pulsing, still adjusting course, Still silent. Sarah put down her phone and walked to her window. The night sky was clear. Stars scattered across the black. Somewhere up there, invisible to her eyes but not to the telescopes, 3i Atlas was moving. And she wondered, is it watching us right now? Does it see our lights, our cities, our reactions? Does it understand what it's done to us? Tonight, October 26, 2025, humanity learned what it means to be visible. For all of history, we looked out at the universe wondering if anyone was looking back. Now we know. Someone is. And the terror and wonder of that realization is still settling in. We built telescopes to see the universe, never imagining the universe might one day turn its instruments toward us, and now that we know we're visible, we cannot choose to be unseen. The object continues outward, the pulses continue, the silence continues, and we wait, changed forever, for whatever comes next. Act 6. Waiting in the expanding dark. It's 2 a.m. now, October 27th, 2025. Most of the world is asleep, or trying to be. But in observatories scattered across 6 continents, the lights are still on. Telescopes are still tracking. Receivers are still listening. Data streams are still flowing. Because 3i Atlas is still out there. Still moving. Still pulsing. Still silent. And no one wants to look away. Not now. Not after last night. Dr. Elena Vasquez is still awake in Chile. She's at the Cerro Tololo Observatory, the same place where she first noticed the brightness anomaly 6 days ago. 6 days. That's all it's been. Less than a week since she saw a data point that didn't fit and decided to investigate instead of ignoring it. Now the whole world knows. She stands outside the observatory building, looking up at the sky. The stars are impossibly bright here, away from city lights, at high altitude where the air is thin and clear. Somewhere up there, invisible to her naked eye, 3i Atlas is traveling, outward from the sun. 1.8 astronomical units from Earth, about 270 million kilometers. Still too far to see without a telescope, but close enough that every major instrument on the planet is pointed at it. Elena thinks about what they've learned in 6 days. The object brightened when it should have dimmed. It pulsed with mathematical precision every 47 hours. It showed coordinated thermal patterns that looked like circuits activating. It adjusted its trajectory in ways that brought it closer to Earth's orbital plane. And then yesterday afternoon it spoke. One signal, 11 minutes. Then silence. Every natural explanation had failed. Every attempt to make it fit into known physics had collapsed under the weight of the evidence. What they were seeing wasn't a comet. It wasn't an asteroid. It was something else. Elena doesn't say the word out loud. Not yet. But she thinks it. Machine. In Cambridge, Dr. Sarah Chen is also awake. She's in her apartment, laptop open, looking at the latest light curve data. The pulse is still there. 47 hours, 12 minutes, 34 seconds. Regular as clockwork. She's been tracking it for days now, watching the brightness rise and fall with perfect consistency, and she realizes something that makes her chest tight. The pulse isn't slowing down. Usually when an object rotates, friction and tidal forces gradually change the rotation period. It might speed up or slow down over time, even by tiny amounts. But 3i Atlas isn't changing. The pulse period has held steady for 6 days. Not a single second of drift. That's not natural rotation. That's something maintaining its rhythm deliberately. Something powered. Sarah closes her laptop and sits in the dark, thinking. If it's powered, it has an energy source, a battery or a reactor or something humans haven't invented yet. If it's maintaining a precise pulse, it has sensors and control systems. If it sent a radio signal, it has transmitters and possibly receivers. If it adjusted its trajectory, it has propulsion. This isn't a rock, this is a spacecraft. And it came from another star. At NASA's Jet Propulsion Laboratory, Dr. David Kim is running one final trajectory update before trying to sleep. New positional data came in an hour ago from Mauna Kea. He plugs it into the orbital model. The acceleration is still there, 0.02 millimeters per second squared, prograde, forward, and the geometry is still concerning. If the acceleration continues at this rate, 3i Atlas's closest approach to Earth in November will shift from 270 million kilometers to approximately 185 million kilometers. Still far. Still safe by any measure, but closer than predicted. And the direction of thrust is too perfect to be random. David saves the calculation and leans back in his chair. He thinks about the leaked memo from yesterday afternoon, the one that mentioned intercept windows and response scenarios. NASA wasn't panicking. They weren't preparing for an impact, but they were asking, what if? What if? The object changed course more dramatically? What if the acceleration increased? What if it stopped accelerating away and started accelerating toward? There were no protocols for this, no defense systems designed to intercept something moving at interstellar velocities. All humanity could do was watch. and hope that whatever was steering this object had no interest in collision. In Germany, Dr. Sophia Lindstrom is writing a report that will be delivered to ESA leadership in the morning. She's trying to summarize 6 days of impossible data in language that's both accurate and diplomatic. Object 3I Atlas exhibits multiple anomalous characteristics inconsistent with natural bodies. Brightness variations, thermal patterns, trajectory adjustments, and radio emissions suggest coordinated behavior. Natural explanations cannot account for the full set of observations. Further study required to determine origin and intent. She reads it over. It's cautious, professional, the kind of language space agencies use when they want to acknowledge something without committing to a conclusion. But Sophia knows what she really wants to write. We're being visited by something artificial, something intelligent, something that's studying us, and we have no idea what it wants or what it will do next. She doesn't write that, but she thinks it, and she knows everyone else working on this is thinking the same thing. At the Very Large Array in New Mexico, Dr. Michael Torres is still in the control room. It's been more than 10 hours since the signal was detected. They've broadcast 3 more times since then. Different messages, different patterns, mathematical sequences, images encoded in binary, even a simple audio greeting. Nothing. The radio spectrum where 3I Atlas sits is silent except for natural background noise. Michael stares at the monitors, watching the data stream, waiting for something that probably won't come. He thinks about the signal yesterday afternoon. The way it appeared suddenly lasted exactly 11 minutes, then stopped. Deliberate. Controlled. Like someone turned on a transmitter, collected data, then turned it off. And the frequency, 1.420 GHz, was chosen for a reason. It was a signal designed to be noticed, to be recognized as artificial, which means whoever sent it wanted humanity to know it was there. But they didn't want to talk. They just wanted to be seen. Michael wonders what that means. Are they observing? Documenting? Cataloging? Or is this something else entirely? A warning? A marker? A message we're not equipped to understand? He doesn't know. Nobody knows. And that's the most unsettling part. It's almost 3 a.m. in California, and Dr. Jill Tarter is finally sitting down after hours of interviews and meetings. She's at her desk, looking at the signal analysis one more time. 40 years. That's how long she's been searching for signals like this. 4 decades of listening to the cosmos, of scanning frequencies, of hoping that someday, somewhere she'd detect something that wasn't noise, wasn't natural, wasn't us. And now she has it. A clear, structured radio emission from an object that's showing every sign of being artificial. This should be the greatest moment of her life. But instead she feels unsettled. Because the signal didn't want a conversation. It didn't offer information. It didn't wait for a reply. It didn't engage. It just measured and left. And that changes everything. First contact, in every scenario humanity ever imagined, involves some form of dialogue, some exchange of information, some mutual recognition. But this is different. This is one-sided observation. And Jill realizes something that makes her cold. We're not equals in this scenario. We're specimens, data points, something to be observed, measured, cataloged, and then, what? The object continues on its journey, it reports back to wherever it came from, it files us away in some cosmic database and moves to the next star system, or does it do something else? Jill doesn't know, and the not knowing is harder than she ever imagined. Across the world tonight, millions of people are awake, thinking the same thoughts. In Tokyo, a businessman stands on his balcony, looking at the stars, wondering which one it came from. In Rio de Janeiro, a mother holds her sleeping child and thinks about what kind of future he'll grow up in. In Cairo, a group of students sit in a coffee shop, talking until dawn about what this means for religion, for philosophy, for humanity's place in the universe. In Sydney, an artist starts a painting, trying to capture the feeling of knowing you're being watched by something from beyond the stars. Everyone processing the same truth in different ways. We are not alone. And now that we know, we can't unknow it. The universe is no longer a question. It's an answer. And the answer is, someone else is out there, watching, measuring, moving through our solar system with purpose and intent. Dr. Avi Loeb is at home in Massachusetts, looking at emails from colleagues around the world. Some congratulate him. You were right to consider artificial origins. Others criticize him. You're jumping to conclusions. We need more data. Avi doesn't care about either. He cares about the truth, and the truth is clear in the data. 3I Atlas is not a natural object. It's something designed, something built, something sent, and humanity is facing its first confirmed encounter with intelligence from beyond Earth. Not a radio signal from a distant star, not a microbial fossil in a meteorite, but an object. Here, in our solar system, moving with intent. Avi writes a single tweet before bed. Tonight we learned we are not the universe's only engineers of light and motion. 3i Atlas continues outward, still pulsing, still silent. Whatever happens next, we are changed. We have been seen. The tweet gets 1,000,000 likes in an hour, because it's true. It's 4 a.m. now. The darkest part of night, the quietest hours. In observatories around the world, astronomers are still watching, still tracking the faint point of light that refuses to behave like anything natural. The object is 270 million kilometers away and getting farther every second. It's moving at about 60 kilometers per second relative to the Sun. In a few weeks, it will cross beyond the orbit of Mars. In a few months, it will be in the outer solar system. In a few years, it will leave the Sun's influence entirely and return to interstellar space. And then it will travel for thousands, maybe tens of thousands of years before reaching another star. Unless it changes course again. Unless it decides to do something we haven't predicted. Unless it's not done with us. Dr. Elena Vasquez walks back into the observatory building in Chile. The telescope dome is still open. The instrument is still tracking 3i Atlas. She pulls up the latest image, a tiny point of light, unremarkable to anyone who doesn't know what they're looking at. But Elena knows. That's not a comet. That's not an asteroid. That's a visitor from another world, another civilization, another mind entirely. And it came here deliberately. She thinks about what happens next. Will more come? Is this the first of many? Are we about to learn that interstellar travel is common and we've just been blind to it until now? Or is this rare? A lone probe from a civilization so distant we'll never meet them? Elena doesn't know, but she knows one thing with absolute certainty. Nothing will ever be the same. The sky is starting to lighten now. Dawn is coming to Chile. In a few hours, the sun will rise, and the world will wake up to the news that spread through the night. People will check their phones, turn on the TV, see the headlines. Signal detected from interstellar object. Scientists confirm 3i Atlas shows signs of artificial origin. Humanity not alone. Evidence mounts for extraterrestrial technology. And life will continue. People will go to work. Children will go to school. The world will keep turning. But underneath everything, there will be a new awareness, a new understanding. We are not the universe's only children. Somewhere in the vastness of space, other minds exist. Other intelligences that can build, that can design, that can send objects across the void between stars. And one of those objects came here. To our solar system, to our neighborhood. And it looked at us. It's October 27th, 2025 now, just barely. The earliest hours of a new day. 3i Atlas is still out there. Still moving, still pulsing, still silent. The observatories will keep watching. The data will keep coming. The analysis will continue. But the biggest question has already been answered. We are not alone. And now we wait. For what? We don't know. For the object to do something else? For more signals? For answers? Or just for time to pass? For the object to fade into the distance, leaving us with more questions than we started with? The light still pulses tonight. Fainter now. With distance but regular. A metronome counting time across the emptying dark. We watch because we cannot look away. We listen because the silence after the signal is louder than any answer could be. 3i Atlas continues outward into the void, and we continue forward into uncertainty. Changed forever by 7 days in October when something looked back. The universe is no longer waiting to be discovered. It has already found us. And in the cold precision of the data, in the mathematical certainty of the pulse, in the deliberate silence after the signal, we realize we are not at the end of a story. We are at the beginning of a question we may never finish asking. What comes next? We don't know. But we will be watching. Because now we know someone is watching us too. And in that knowledge, everything has changed.